Morning, friends. I'd like to welcome you all in this Saturday manufacturing talk. You all know that every Saturday, 8:30 p.m., we are, conducting this webinar series. We started long back. We are coming close to 6 months right now. So it is the 24th week, and this particular webinar series we discussed about the advanced, the concepts which are getting used in the manufacturing field. We have the speakers previously in the field of modeling and simulation, in the field of industrial robotics, and the additive manufacturing. And today we are going to have an interesting topic, which is the digital twin. You all have heard the term called the digital twin, which is the digital replica of the physical, the system. And some problem is there. Yeah. So, the digital twin is becoming very important in the manufacturing domain, specifically to get to know about the process quality in the real time, and also how the process will behave, how the process will be occurring if we change the new environment. We are very much also eager to know the health of the machine. So the digital twin also pertains to the machine itself. It's not only the health, the process monitoring, it is also for the health monitoring perspective. Now, today we are very much privileged to have Professor Dariusz Ceglarek from University of Warwick in the UK. Professor Ceglarek is a member of IEEE, and he has received the PhD degree in mechanical engineering from University of Michigan and Ann Arbor in 1994. He was a professor at University of Wisconsin-Madison. Currently, he is the EPSRC Star Liquid Chair, Research Chair with the University of Warwick, Coventry, UK. He has been a principal investigator and also co-investigator on various research projects of worth £30 million. He has authored and co-authored more than 200 articles and is listed by Stanford University among top 2% of the world's leading scientists. His research interest includes smart manufacturing and data mining AI for root cause analysis across design, manufacturing, and service. He is also a fellow of the College International Portland Research in Productive in CIRP. He was a recipient of several Best Paper Awards, 2018 JLR Innovista Award for the most innovative biologic technology, the EPSRC Star Award, and the NSF Career Award. He was Associate Editor of ASTM Smart and Sustainable Manufacturing Systems, IEEE Transactions on Automation Science and Engineering, and also the ASME Journal of Manufacturing Science and Engineering. So friends, you can see that Professor Ceglarek has got, the huge expertise in the field of smart manufacturing, data mining, AI, the root cause analysis and all. So everything which are the backbone of creating the digital twin. So let us hear from Professor Ceglarek about the digital twin of for in-process quality improvement of production system. Professor Ceglarek.
Thank you very much, Professor Paul. It was a pleasure to be. Thank you very much for inviting me. And it's a pleasure to be with all of you, actually. Not face-to-face, but in current environment, just digital is through the screen, but it seems sometimes it works better. I will share my slides. Let me just see. We did... yeah, if you can...
Yeah.
Can you see it?
Yeah, it is now. You can go to full screen mode and.
Okay. Yes, there is a full screen. Do you want me to go slideshow because we have some challenges last time?
Yeah, you click that one.
Yeah. But tell you what, if we have some challenges, but can you see clearly, or I can?
Yeah, we can see clearly. Yeah, you can go ahead with this also.
If Okay.
It's fine.
Yeah, it's fine because sometimes
Yeah.
depending on which screen I have two monitors. Okay, can you hear me well? Maybe I've just.
No. I mean, your audio is absolutely clear.
Okay, perfect. Yes. Okay, so I tell you what, I have a few screens. I'm not looking at you, but looking at the other screen. But just in case, if there is any connection problem, I probably turn off my camera just to make a little bit easier from network point of view. If there is a need for that, actually, or if you cannot hear, please let me know.
Yeah, sure.
Yep, that would be good.
Yeah, so far so good. Yeah.
Okay, perfect. Yeah. So again, thanks a lot for inviting me here. So today I just want to look from perspective of, let's say, simulating a digital twin, but it is a little bit different digital twin logic, which in maybe classical way. So in other words, looking at the simulating processes under the uncertainty of manufacturing. In other words, with stochasticity embedded. In other words, modeling process with embedded errors as it occurs during the production. So that's actually my understanding in this context of digital twin. And just to show the purpose of this simulator, this digital twin, we are looking from point of view of quality. So we would like to predict the quality defects, which is embedded or they are caused by, let's say, different stochastic errors as occurs because of the product, for example, part tolerancing, part variation, as well as during the process, tooling, fixturing, robotics errors, and so on. So that's the logic a little bit from point of view of the purpose. So going towards the quality improvement. And on top of that, we are using also the data. So we are doing simulator, but also embedding the real data. And the goal is to embed the quality data which are captured in process. What I mean by that, I can capture data, as you know very well, offline. For example, I can have a CMM machine or scanner, which is in a CMM room or separate, let's say, a facility, metrology lab, and I'm measuring components. Or I can have a measurement gauge in production line, for example, not in assembly station or not in manufacturing specific station, but in separate metrology station, which is already in production line, directly in production line. So there's inline, what I would call it, inline measurements. And the third level would be if I have a measurement gauge directly in the station when I'm conducting specific manufacturing operations. For example, in assembly process or in welding, I can capture the data directly during the welding process. So that's what I mean by in-process data. So we are trying to develop this digital twin from point of view quality improvement, embedding the in-process data, and also going, not necessarily quality understood as a monitoring, for example, classical SPC, statistical process control, but going towards improvement. And what I mean by improvement is going towards root cause analysis of the defect. So we try to identify the process parameters which are, let's say, causing some of the defects understood in quality sense. So for example, increasing the variation, Six Sigma, and so on. So looking at the root cause analysis and then providing basically strategy for corrective actions and preventive actions. So that's actually, we are doing analytics from this perspective under the digital twin. So digital twin include all of these elements, processes, design, data, real data, as well as basically the strategies for root cause analysis and corrective action. So the purpose of doing this, we would like to use this digital twin not necessarily to simulate on specific stage or phase of new product introduction, but to use through all of them. What I mean by new product introduction, I mean by basically by design, launching a new production, and production. So in other words, using the one digital twin, which has the capability to be scaled from design to launch, ramp up of production, as well as to the full production. That's the logic behind it. And the purpose of that is to be able to look or increase this right first time. In other words, eliminate or reduce number of engineering changes as they occur during design, and also eliminate defects as they occur during manufacturing. So that's the kind of logic which is I'm going with this presentations today. I am, as Professor Paul mentioned, I am at University of Warwick. Some of you who, if you are not familiar, we are basically in the geographical center of England, not on UK, but of England. So we are basically located in close to Birmingham, between Birmingham and Coventry, actually part of the Coventry, which was before was the center of the automotive industry. The department or University of Warwick is a normal standard university with probably 25,000 students currently. But the WMG Warwick Manufacturing Group is not typical academic. It's academic department, but it was not typical. It was founded by Professor Bhattacharya, who was also alumni of Kharagpur, IIT Kharagpur, sometimes ago. And then actually bringing the two different things, actually bringing the academic, let's say, faculty in classical standard way, professors, associate professors, assistant professor, but also bringing people who are outside of classical academic. So we have a total of probably 600 in our, not in the university, but let's say looking from point of view of our WMG academic department, we have probably 600 roughly staff, not only professor, associate professor, and assistant professor, but we have a number of different people working with industrial partners on different programs and also large educational programs. So we are providing the teaching outside, probably in a couple of different countries, 5 countries or so. So we have quite a large number of activities with industry. Actually, overall, we have also we are part of the UK High Value Manufacturing Catapult Network, which is an industry university, but not an industry university, but it is helping UK and not only industry specifically to, let's say, accelerate the taking innovations. So we are basically one of the 7 centers, the only center at university. Actually, so that's actually give us some background a little bit about WMG. And then from the area point of view, we are spanning a little bit different areas from energy. I will not talk too long about that, but just to give you some ideas what I mean. Basically, it's not a typical academic department because we have people on energy side looking from point of view of battery, electronics, powertrain, but also looking at the intelligent vehicle, mostly looking from point of view of autonomous vehicle connectivity. So there's a number of different tools which is used to make this autonomous vehicle. We are building, for example, this road between Birmingham and Coventry for vehicle for a road between Birmingham and Coventry for autonomous control. We have a number of groups looking at the digital technologies and which is bringing the AI people, computer science people, and also the healthcare areas, and also materials and manufacturing, which is, I am sitting in materials and manufacturing, what we call ourselves digital lifecycle management, bringing data and simulation of the processes, methodology together. So that actually gives you some ideas and flavor a little bit about the WMG. So it's a good way for me to collaborate because we can collaborate with a different level of different people. I think this, just want to show you, this building was open. It's a Professor Bhattacharya building right now. It is called, let's say, which was open probably 1.5 to 2 years ago for purpose of collaboration with industry. So bringing kind of like a center for automotive innovation in UK. So we have OEMs, tier 1, tier 2 companies working together basically on different innovations. This is on campus. So this is a co-location of university and industry actually directly on campus. And then from my point of view, maybe let's think as the Professor Paul was mentioning, but my interest is looking from point of view of integrating data. So classical way, looking from the methodology point of view, capturing different in-process data, looking at the data and data science I put here, but classical, we use the statistics for a number of years. And for the last few years, looking more on the AI, deep learning type of activities, since not the, because the performance, what we did sometimes in 20 years, trying to find the statistical approaches, this can be done in 3 months by PhD students, getting the same performance measure by using, for example, different deep learning tools, like, for example, convolutional neural nets or reinforcement learning type of tools. So this is actually becoming quite an interesting transition of the methods approaches, which is available actually right now. And on top of that, what we are bringing not only data and data science, but also linking with the physics-based simulation. So we are bringing basically computer-aided design, computer-aided engineering, for example, to simulate it or multi-physics simulation for defects, for example. So depending which process, if you look at the processes of assembly, automotive assembly processes, looking from the deformation of the components, or if you look in the joining side, simulating of the joint itself, actually. So we have quite a lot of work actually in laser side, laser welding, for example. I know that you have EMPs and as a friction stir welding. So there is some kind of potential, let's say, synergies between both sides, actually, from our point of view. So bringing these things together for what purpose, actually? So as enablers, we are using different aspects of sensor fusion, different analytics, signal processing, machine learning, which I was mentioning. And then the driver for us actually are looking from accelerating design, make, test, and scale up. That's actually our main goal, actually, from point of view of development, right first time type of acceleration, and looking at the zero defect, zero waste logic. So this is actually our driver, which is overall we're looking for. And this is especially with application to e-mobility right now. As you know very well, is e-mobility. What I mean by e-mobility is looking from point of view of, for example, battery electric vehicles, the BEVs. Actually, it is becoming a quite big transition for automotive industry overall. And then with UK policies right now trying to stop production of internal combustion vehicles by 32 or 35, 32. So it looks like many countries actually right now looking from this clean zero net type of logic. So this is becoming quite a lot of pressure from designers and manufacturers to deliver basically this product into within the cost, with performance, as well as with high quality, actually, because they are quite sensitive. So that's actually our driver, which we're looking from point of view. And our classical application area, so we look at the CAE simulation, data mining aspects, actually from specifically applying to tooling, modeling, design, variation simulation analysis, or robotics cell. And then we already mentioned root cause analysis. And then we are using these different CAE tools for lightweight manufacturing. So for example, looking at the joining, laser, robotics, quality inspection, or reconfigurability resilience processes as lightweight, and also lightweight, but as application to e-mobility. So our expertise here on e-mobility is looking at the battery cell, for example, cell contact lattice, battery module, cell to bus bar casing, battery enclosure. So you can see going through whole perspective or whole spectrum of e-mobility. We are not doing the specific cell itself design, but assembly processes of the battery cell, yes. And then let me just bring this, what I just mentioned, a couple of different things in the context of Industry 4.0. So then I will give you an example how we look at this, how we fit to Industry 4.0 from our perspective, and also how some application of the work which we have done it, especially looking from this digital twin area. So just give you our perspective, our interpretation of Industry 4.0, the way how we understand it, actually. So I'm not necessarily reviewing the Industry 4.0, but just want to bring you, which all of us probably already are familiar quite well, from Industry 2, Industry 3, Industry 4.0, from mass production to computer automation, and going right now through a number of different enablers, in cyber physical system, IoTs, Internet of Things, cloud computing, and so on, actually. So there is a lot of different enablers which are being developed by a number of different groups, including basically Professor Paul's group as well. So there's a worldwide actually activities going on. So from this perspective, the way how we interpret and looking in this evolution or this transition basically through the different industries, and I will show you where we fit into it, is, so my understanding or my looking at this is that this transition is, you can look at this through the objectives and solutions. So if I look at the objectives, this objective are changing continuously, starting from the cost, for example, which historically was, which we know very well from Henry Ford a long time ago. Then actually it was the quality as objective was added. And this quality actually, which was mostly started, initially by Toyota production systems at least in automotive industry. So it was quite strong, but does not mean the cost was not important. So there was cost plus quality. And then there was a number of different solutions which was developed during the years as it was developed. And then from objective of quality, suddenly people want to have not only good product, but they want to have a variety, increasing its variety. So this variety is increasing. And there's a number of different talks about the flexible manufacturing system, as you might be very well familiar. but the objective was variety. And then there was a number of different computer-based tools which was developed in the times, and this shifted to next one. Now, I don't want to have necessarily only the variety, but I also want to have responsiveness. In other words, systems or products, production systems can be responsive very quickly to change, for example, from one product to another product. So it's becoming a time issue here. And this actually, you know, I was lucky being in Michigan when ERC, Engineering Research Center, on reconfigurable manufacturing systems was probably the largest program, not probably, it was the largest manufacturing program in US actually in that time, looking and driving the configurability of production systems. So there was responsiveness actually with Yoram Cohen driving it. And there was a number of tools again developed, kind of looking from point of view of models, CAD, CAM, CAE. I'm just giving you very generic statements here. So this actually is probably 2000 roughly. I'm just putting some dates here. And then actually right now, in our opinion, things are going to the next step, perhaps looking what I would call it resilience aspects, which is happening that the objective becoming, I don't want to necessarily, I would like to have a responsive system with large variety of product, with high quality and cost, but I would like to have a near zero defects, not only for product, but in life cycle of the product and production system. So they're actually looking from this resilience as the near zero defects in life cycle. And there's a number of different analytics being developed for that purpose, actually. So here, the way how we fit it is probably looking for more on this resilience side at this moment. And the purpose of doing this from our side is, instead of, for example, what Yoram Cohen called as a reconfigurability from exactly the capacity and functionality needed exactly when it's needed, which was more on the reconfigurable manufacturing system logic, going towards the capability to self-recover from product lifecycle failures and changes. So that's actually logic a little bit, which we follow. What does it mean from perspective is looking at the simulator, which is bringing the life cycle, meaning design, manufacturing, and services, actually, and developing the digital twin or simulators, which are precise. What I mean basically by that, they are linking, they are modeling the product, non-ideal products, non-ideal processes, not focusing on the product, which is, let's say, ideal, meaning everything is as CAD as design intent, but looking from perspective of non-ideal, real basically scenarios, and embedding into the simulation directly, which is becoming a little bit complicated situation because you have a lot of computational problems, challenges. Model basically is not a perfect. So this actually is quite a number of different level of challenges which need to be resolved. So that's actually what we are trying to achieve actually from the perspective of our perspective, the way how we look at this stuff. And then how do we fit and what we want to achieve? So I'm giving you just perspective how we go in this journey. So some of you might be familiar with let's say V model. So this actually is kind of V model, which is used for new product introduction. So NPI, some people call it, in short. So from new production system or new product introductions, starting from the left side with customer needs and the cascading requirements as they go on design side, and then realizing it slowly through building, prototypes, more mature prototypes, pre-production, pilots, production, and finally end up in production actually. So that's actually the model. So I was have a chance to be part of the back in US of the program which was looking at the analysis of digital tool available for NPI, for new product introduction, within automotive and aerospace. And then actually surprisingly, so this is coming from this report actually, which was completed. And then actually surprisingly, there was classification of the tools, digital tools. So mostly looking from digital tools perspective only right now. So from perspective of saying, are these tools available commonly, green, or these tools are emerging, or not available at all? By emerging, I mean they are in the industrial labs or research labs, universities, institutions, and so on. So surprising was that there is a lot of tools which is not available. So there is a lot of tools which you might be familiar, bill of materials, engineering data. So there is quite a mature already, but number of different digital tools. I'm talking about only digital tools, which was not available in early design stages, and also in product validation in the late stages. And there was not too much links happening between the requirements and the production or pre-production stages. So that's actually, it is a link which we are focusing on from our perspective. So the way how we look at this, we are looking at developing this closed loop system, which we are closing basically requirements with pre-productions, non-ideal scenarios, as in non-ideal, I mean non-ideal products and non-ideal processes to bring them together. And that's why we call it here closed loop. An ideal case in process data, we want to use it. Why? Because it's a time of assets. So there is and sampling, of course. Sample sizes, actually, I cannot get too much data if I have to move the parts from the production line, for example, to a CMM room, to metrology lab. So that's actually the logic which we are following it, looking from design stage right first time and looking production side near zero defects as a target. So it's coming back to the three ingredients, which was already mentioning, how we do this. And the way how we formulate it, actually, is along, for example, if you look at this right chart here, we are formulating it in such a way that we are going from the product and process design. So looking at this as a right first time objective, looking in the factory side, which is looking at the real-time optimization in the factory, and looking in the product in field as well. So we take a data. And then actually, if I look at this kind of generic three boxes here from design, production, and product in the field, in service, we are basically capturing the data from both, from production as well as from the product. So we're looking at the analytics on the inline monitoring. We developing the multidisciplinary defect simulator. So we are modeling the simulating the defects. For example, laser welding is one aspect of the formation of the components in assembly station. Then actually what we do, we develop basically a linking with the root cause analysis and corrective action, preventive actions module, which is mostly the AI. So we are integrating AI with the defect simulator and with data combined. So we are using the AI tools for analysis of the simulated data or analysis of the real data, both. So no difference for us. We are trying to basically make us synchronize in such a way that it's no difference. So we are having this loops here. Therefore, we are having this, for example, simulation in closed loop, meaning we are bringing all of these aspects. If data in design is not available, we are using simulation data, and then we are simulating, but we are simulating production, not simulating product, not simulating process as a ideal, but simulating production with these embedded errors. Or we are doing quality in closed loop, basically, through the corrective actions and preventive actions. If the system allows, can do be correction done automatically, if not, manually, basically. So that's the logic. And also in monitoring side, what to measure, how to measure, and where to measure, basically, is a challenge. So that's our framework. How does it work right now? For example, if I, oops, sorry, I went too far a little bit, just give me 1 second. How does it work? For example, from the way how we look at this framework overall. So our goal is, already what I mentioned, shortening lead time as a business goal or industrial intention. Business looking from the increasing right first, so lead time, which is right first time, looking from the installation commissioning time reductions, but also from ramp-up time, new production ramp-up time, looking at the shortening mean time to detection, defect detection, and shortening mean time to resolution, defect resolution, corrective action. So that's actually the overall targets from the goal point of view. And then what we try to do on these three different loops overall. From our side, basically, the way how we look on the simulation closed loop, development of this digital twin with embedded CA simulation, which is a simulating of the physics of the processes with data, and specifically focusing on assembly processes in our case. So we're having sheet metal, deformable part, extrusions in automotive aspects, for example, body-in-white automotive bodies or batteries, cell, battery modules, battery enclosures. And that's aspects of first aspect of the simulation side. We're also looking at the monitoring side. So mostly focusing on the configuration of the in-process measurement data. So it's robotics measurements done in process or inline at least. That's a kind of logic from our point of view. And then quality and closed loop, specifically developing analytics, linking both digital twins with the data for the purpose of the root cause analysis or root cause driven corrective preventive actions kind of logic. So that's a journey which we are taking. How this potentially can be, and what's the advantages here, which is the way how we see it basically, and then the way how we're driving this forward. We would like to have a simulator which is used for different maturity levels. So it's NPI I mentioned earlier on design stage and pre-production stage. But we want to use, for example, digital twin from point of view of the lower TRL level. So for example, in design stage, let's call it in this way. So we're doing the simulator part in design stage. But for example, in design stage, since many of you are doing the joining welding, most of the people using for example, using coupons to assess basically welding process. And my understanding is that quite a lot of work is done in your center on the welding side. So let me just give you one example, which will be easier to follow what I mean basically by the scaling up here on this vertical direction. So if I do coupon checking or testing, nobody's producing coupons later on, and people are producing the whole sub-assemblies. So if I use, for example, coupon on this level, the results, the errors between the coupon and the real sub-assembly can be 15%, 20% or more in many cases. Why? Because you have a different geometry, you have a different heat distribution, you have a number of different things which cannot be replicated one-to-one. So what industry is doing, they are doing coupons and they have challenges to fix it. So we try to simulate this. So we are already simulating basically on coupon levels, but also scaling up, for example, simulator, which is allowing us to scale up to the real geometries, which is not coupon geometry, just as example. And then from demonstrator on scale up the simulator, for example, demonstrator going to the pre-production pilot. So we're also going with our simulator to industrial setting when suddenly we have a different scale up. So we don't have a geometrical scale up in the first two steps, but we have, for example, the stochastic scale up. We have a production samples that's increasing rapidly, and then we would like to have the simulator be able to handle basically this sampling scale up. So we have a different scale up. So you can see this, we're looking from the two different directions actually on the scale up, such a way that the simulator digital twin is used as we go through NPI, new product introduction. So what does it mean more specifically what we are simulating and doing on these different stages? For example, on the first stage, which is design stage, I put here TRL, technology readiness level 3, 4, but design stage. We are simulating basically the whole assembly cell. So we're not simulating using joining as example. We're not simulating coupon testing and so on, but we are simulating all three things together: fixturing, tooling for whole sub-assembly, robotic basically, and then aspects and laser welding, for example, in this specific case. So we are bringing the three things together, not one by one independently, but three things together to be able to consider the scale up in terms of, for example, geometry aspects as we move from coupon to the final sub-assembly. Then actually what's happening, the scale up here, basically, we are also considering the on demonstrator level, for example, when we have in our lab, is the whole sub-assembly at this moment. We are also considering basically data coming. So we talk already in process data and simulating the in process data as well in the simulator and using the real data to be as a correction part. So this is actually the second level, and going further with that purpose, for example, to pre-production pilot, this is coming on industry side, that suddenly we have a sample size is increasing. So we are taking basically enhancing the same simulator which you use on the first two stages to be able to understand production defects and corrective actions of the production. So that's generic statement. And then we're using a number of different tools on multiple levels. I just listed some of them to give it some flavor. But for example, on the from point of view of design, using different level, different optimization rules, basically using different aspects of on the demonstrator level. We have to put here basically some model, but there's much more here. And then using more and more AI-driven, actually deep learning-driven type of tools, basically on this last stage, which data is increasing rapidly. So that's give you some kind of generic directions of the travel. What does it mean right now as example, actually, from point of view of what is it? So I'm giving you just example of what we did, the simulator of the assembly station, which is most looking at the remote laser welding of the door. The door actually is industrial door already. And then actually we are developing, so this is a simulation in our lab. So, well, from point of view of visualization, there's a lot of different commercial tools available for VR and AR. And I, honestly speaking, is not the key point here. Key point here is not this picture that you see here, which is showing basically the process, but we are embedding the errors in the process. So we are embedding the part deformation. So we're not considering the part as CAD model coming from the CAD CAD model, but we are considering part deformation, real parts. And not only one part, we are considering batch of parts. So we are considering basically production emulating. So we're considering the production sample sizing as we are producing with errors embedded. And then we are designing the fixturing for this non-ideal batch of parts. On top of that, we are simulating basically the errors of the robotics and welding processes on top of that, in such a way that we have a fixture model We have an offline program and joining processes, but also we have a joining process specifically with parameters embedded. So everything's under errors. What is it helping us to do actually? So here I have a picture, but actually we are bringing all of the three things combined together. Here's just a snapshot from the software, which is showing basically different capabilities. So if I, for example, here's just snapshot, I don't know if you can see clearly, but showing basically clamps. And then if I move the clamps, I can see what's happening with the errors as they go around the parts and components. So we can play around with different scenario configurations. This happening automatically or manually if somebody prefer. Basically determining the tooling location and the different errors. We can also consider temperature distribution as well, or deformation, mechanical deformation of the part. So this, by doing this, for example, which allowing us to do this right first time. This gives you an example of this door, for example, which we developed. We work with the companies. This is a real actually application. This, by the way, this door is getting to production this year, right now. So we went through the whole cycle from design concept, developed the whole process, and it's getting to the production cert. It's already production certified. And by the way, the remote laser welding for this door for aluminum parts is a second application worldwide. First application was in Audi. So Audi so far has the only was able to do this. Nobody else is able to do the productions for aluminum components in mass production of like automotive production systems. So this is the first application. Only the Audi did a very good engineering job by developing the process. We have not developed the process. We have developed the tools which allowing us to develop the process, and then using these tools we develop the process. Audi could put 50 engineers working on this. We couldn't at the university. So we did basically whole ball game here by ourselves, basically by developing the tools, and therefore we could speed up the process much faster. So that's a logic a little bit, just to give you some ideas and the challenges. Maybe just one word on this remote, because remote basically is, it's one-sided, non-contact, as you probably might know. Therefore, actually a much less constraint for design people. I don't need to have a two-sided contact when I have to have access from both sides and I have to touch the part. Here, we don't need to touch the part from both sides. However, challenge is that if we don't squeeze these components under error conditions, the gap between components is changing. If this error gap is changing, suddenly there is a lot of defects if you cannot consider this. So without having good digital simulator of doing this, becoming a challenging task. So therefore, actually, by implementing this industry, just give you some ideas, how many for the same process or similar process, but on the steel, not on aluminum side. So steel is easier to handle. The industry is doing it today on daily basis. So we work with one large integrator, and they basically develop the same tooling and check, and we develop parallel the same by using simulator. They have, let's say, if you really look, we are able to eliminate, they have 100 changes, tweaks in the one assembly stations just to make this process feasible. So we're talking about this one cell to make this process feasible, how many tweaks, changes they need to do it to be able to make it work. So we have not only feasible, we can do it with the 2 changes, actually, honestly speaking. And then actually instead of 100, and they got a feasible solution, we got optimized solution. So performance is better overall. So you can see, give you some ideas, potential impact, which might be of this simulator to have in the place. Why is this reason? I'm switching to aluminum right now because we couldn't get aluminum. Nobody has it except Audi. So aluminum is completely open. Aluminum meaning remote laser welding of aluminum, let's say, assembly parts in automotive industry was not used in the days. So from point of view aluminum comeback, we can make a joint, just give you some ideas. So for example, there are 2 components, 2 parts with the gap 0, and you have a nugget, like have a joint. Well, when gap is increasing, which is happening very often, all the time, 0.4 millimeters, we can still make basically the joints. If gap is increasing to 0.8 millimeter, we still can have a make a joints. So we can make basically optimize the process parameter on the fly in such a way that we compensate for this variation as it is coming, for example, from the part-to-part gap. One example. And then we can compensate probably 50% of the gap. We can compensate 50% of this, let's say, top surface errors as can be compensated. So this give you some ideas. So this is actually 5,000 aluminum alloy for some of you who might be interested. So this gives you some idea. On top of that, what we can do, not only the gap variation, but we also went to industry. So this is actually coming, this is our lab actually, initially, but we, for example, Sorry, let me turn off the sounds. I don't know if you can hear it, but I can hear it. So I just turn off the sound. So what we did actually, we work with the industrial partners. So this is becoming again a real application of the door. And suddenly we have a 4 meter per minute as a speed requirement coming from OEM. Then OEM said, what about we can do 6 meter per minute? Why? Because suddenly our layout, their layout, production layout change, and they have to consider much faster process, 6 meter per minute. And by the way, you guys have 2 weeks. Can you do it? Normal situation, you will have to repeat all development from coupon starting step by step to get fixture design and so on to be able to increase the speed if possible. So we have this was done actually in 2 weeks time frame without any coupon changes considered actually. So this was giving you some ideas about the scale up. Actually, if you have a simulator which can consider a number of different errors, then actually we can do speed up the development process. For example, changing the speed, as example, changing the cycle time. Cycle time change happen often in design, and then probably people have to figure out what to do after the fact information. So this gives you some idea. So therefore, actually, overall, this simulator which we went through the design stages. We went through the, let's say, monitoring on the development stage, on the monitoring side, from quality control side, which I didn't mention too much, actually. We did demo, and then also what we did here, I can show you the video, we did pre-production pilot. And here again, one more aspect of that is not only the cycle time was changed. Suddenly industry said, by the way, we need to run basically 3,000 parts. And we developed the process for the door, but they said to us, we don't have a door. We don't have it, but we need to run 3,000 to be sure that our durability, reliability of the equipment, everything is set. So we need the 3,000 tests, but we don't have a parts. By the way, we have other parts. They have a dashboard, different shape, completely different parts, and by the way, different material even. And to do it, you have 3 weeks to prepare everything. Can you do it? Can you help us to do it? So you see, this is the reality, real industrial change right now. Suddenly they need to do the test of 3,000. They need to check the technologies mature. They don't have a part. They don't have even materials the same. And can you help them to do it? So this actually was, if not simulator, is becoming a project by itself from beginning to end. So that's actually the logic which giving you a capability potential with providing this, let's say, this digital twin simulator part. And so this is already certified in production right now, probably this year and so on. So our logic overall, what we do, looking from the root cause analysis of Six Sigma faults, defects, which I mentioned, we are looking from the point of view of this quality aspects in closed loop, in process, corrective action, but also we did, which I didn't talk and I will not talk, looking at the quality aspect for no fault found failures. In other words, no fault found, no defect found scenarios, which allowing to measure the defects, which, for example, customer or nobody can see any problem. So customer is complaining, you check basically the programs by service center, everything is fine. So that was actually our problem, which we work with Motorola, but this is a topic by itself actually on the separate issue. Our journey, and I will finish just very shortly, just to give you some ideas. I just show you basically from industrial side the impact, but there's a lot of tools behind it. So industry was interested, for example, in specific applications. So they said, we would like to have this developed process. Can you do it for us? And then they have a number of different advantages here, actually. Lightweighting, for example, they reduce the weight by using this design. They modify the design with this material and with this process, actually. So I cannot show you all the number, but let's say there is a gain of 4.4 kilos of the weight alone because of the materials. And then actually from one side. On the other side, we developed the tools, which we did actually workshop with industry. So asking them how change. So it's a one-day workshop with a number of different companies, looking from, is it something which is incremental change, I think step change, a significant change? And by the way, do you have it? Is existing already? Or is existing but is limited use, or existing not use, or does not exist in my company? So for example, people from BMW, Rolls-Royce, and Constellium, material manufacturer, are saying basically it was significant change for them, and they are not aware of these tools at all. So that's the logic. Last slide here, and I stop on this. Actually, it's 44. We are moving right now more and more on the battery side. So we develop, I show you this door process. We did right now, we are kind of, our target is, let's say 2025. We'd like to develop joining process for e-mobility. And then we have a portfolio of different projects looking at different aspects of that. on different TRL technology readiness level to moving forward with application of different simulators for e-mobility, basically for batteries, battery enclosure, battery cell, battery enclosures, and also linking powertrain to the body structures and everything lightweight, so it's mostly aluminum and multi-material, dissimilar material right now. That's our target and launching. And I guess I stop here. And if there's any question, I'd be happy to answer or to discuss more.
Yeah, so thank you, Professor Ceglarek, for your nice description about the digital twin in life cycle management, the oriented work. You have given us a very brief introduction about WMG and also your research group. You have talked about the digital twin for the in-process, the monitoring, quality improvement, and many more fields. You have given us the introduction about your research group working in the field of the lightweight management, lightweight, the welding of the dissimilar material as well. There will be some questions in the chat box, but before I proceed to that, I do have some questions from my side. So let me put those things first. You talked about the digital twin. When you talk about the digital twin, as I mentioned at the beginning, it could be for the process monitoring and it could also be for the health monitoring. So are you working in the field of the health monitoring aspects of the equipment?
Could you say it again? Equipment, production equipment, you mean?
Yeah, so the welding equipment, like you are assuming that the welding equipment is welding machine or the instrument is the working fine, and yep. Based on that you are trying to control the process. So are you working on the health of the welding equipment or the welding machine?
Oh, I see. We are not working on the fault of equipment itself, so mostly focusing on the product or processes, the both. So product understood as assembled parts and process understood, for example, as a welding process. So we are not working specifically on developing the correction of the robots or welding heads or the fixture. No.
Yeah, I understand. I've got two more questions. One is that you talked about the hybrid digital twin. So hybrid digital twin takes care of both the data and also the physics-driven model. So how do the plugging in the physics-based model real time along with the data model?
Yeah. So maybe as a way how we look at this, let me show you one slide. Actually, I didn't talk about this at all, but we have a simulator. So we have, I didn't show it, so I don't want to necessarily, but I'll show you this part. So we have a simulator of the cell, which includes the fixturing, robotic side, parts errors, and the laser process. We are able to simulate this. So we have a simulator, which we call it variation response methods, which is, again, I didn't discuss the details of that, not at all. So we have a simulator. This simulator allowing us to generate, for example, if I provide the input, I will give you parts, the fixturing, let's say, detailed input of the assembly cell, we can get the output in terms of quality of the component, assembled components. So we have a simulator which is working right now, which we are using it. And then actually, we are using the simulator as a data generator. So we can use the real data, or we can use basically the simulator for generating the data of product quality. So having this data right now, afterwards, we have a second simulator, which is looking from the AI type of tools, which is taking the output, for example, the product quality, and going backwards, identifying the process parameter, which are responsible for this output, especially detecting some abnormalities or specific fault patterns, which we predefined. So this actually, from this inverse, is a challenging task. Before we use statistics, statistics has a problem with ill-conditioned systems. There's a lot of collinearities, a lot of different ill-conditioned scenarios. So we are using the AI. So these two are working together. Then we combine them together. So we have our SCA simulator, which is a variation response methods approach, which is generating the data, and then we are bringing it with the AI tools to be able to go backwards, basically, to identify basically process parameters. That's the logic which we are using.
Yeah. So one more question is that you have talked about the gap the identification for the welding, and based on the gap, you are trying to optimize the weld parameters. Now, when we talk about the weld gap, so are you only measuring the in-planar gap or the out of the plane gap? That means, are you capturing the image only from one side or from, let's say, the multiple sides, depending on the gap in the X directions and the Y directions?
So we model basically two things. We on simulation part, we model basically out of plane, and in real process, we're also measuring it.
Okay.
So we are measuring basically in process. So in other words, we simulate basically up front, such a way that we know basically process parameters, how they change with different gaps. So we're able to simulate it. Then actually we are embedding these corrections into the process, into real machines. And then we're measuring basically the gap as well and adjusting the process.
Okay.
Yeah, so that actually we do three things. Sorry, just two things in the same, not the same time, but these two things. Now, simulation part.
Yeah. So there are some questions in the chat box. Let me those.
I think somebody was saying to put a bigger screen. Actually, sorry for that. I didn't see the chat here.
It's Dr. Gupta from USA. So he has mentioned the latest Shinkansen 700 series has to weld aluminium and lithium alloy car body in a huge vacuum chamber. How does Audi weld its car?
Sorry, which material? 5,000, 6,000?
So it's mentioned that I can't actually read the questions properly. Can you see from your side? Chat box?
Maybe one second. Let me just chat. Yes. Okay. Yeah. I see right now. Okay.
Yeah. Can you just read the question?
Okay.
Yes. It's not properly seen.
Okay. So I'll tell you what. I think there's a questions from Professor Dev Gupta from Motorola talking about the series aluminum series 700. Lithium alloy carbon in huge vacuum chamber. Okay, we do not do vacuum chambers. We don't do at this moment. Let's say, so maybe just, okay, clarifying with the Audi and what we do here. Right now, the goal was not to use any filler wire, if possible. For some materials, doable. Not to use, let's say, an inert gas, in other words. So this was done by naked laser without inert gas and without filler wire for 5,000, which we did before. Audi also did the 5,000, so this was doable, and it is doable right now. For 6,000, we're also doing it for sheet metal without wire and without inner gas for 6,000, but not for all material. For high strength aluminum right now is becoming important, actually, but no inner gas can be done. From point of view of vacuum, we have some discussion, but not in this case, not in this specifically for lithium, aluminum lithium alloy. Why? Because it's expensive, actually. So from our goal is we would like to have a naked laser only, if possible, with minimum, let's say, so no wire if not needed. So we are driving towards basically minimum number of additional components, such elements, such as, for example, wire or inner gas. We are having the vacuum right now chamber welding, but for different purpose. To weld basically the chambers using laser, which has a vacuum inside. So that actually question to us is more how we can weld situation, for example, let's say in refrigerator industry. So how we can make chambers, basically containers, which has to have a vacuum inside, and can this be used by using laser welding without inerting or inserting any gas inside. So we have not done it with vacuum chamber in the context which you are saying here. And Audi has not done it as well. But it's a 5,000 aluminum, which is a different scale of problems.
Yeah, Professor, the next question is that from Mr. Saurabh Tripathi, does scaling up the simulation across various levels increases the cost of simulation?
Okay, tell you what, the cost of simulation in terms of the time, yes, definitely. Cost of overall, no, because I prefer to simulate it if I can, than actually to do the in metal and checking, testing, and through the building physical prototypes. So we are trying to do the physical prototype build as everything is fine, actually, with minimum changes needed. So cost of simulation is probably not a major challenge at this moment. However, there is a high fidelity logic, high fidelity simulation versus low fidelity simulation. So I didn't talk about this, but there is we are balancing between high fidelity, which is a slower process but more accurate, and low fidelity, which is faster, less accurate. So right now, pending what I mentioned about the scalability, I didn't get into details, but this is actually a trade-off between the high fidelity and low fidelity. So from our side, we don't see cost of simulation in terms of let's say, time is doable. In terms of the cost understood as a computer hardware, well, definitely yes, because we are using the different clusters to do this job, depending how high fidelity simulation is needed. So, but it's not the cost which we take into consideration at this moment in terms of, if I understand correctly, the question.
One more question is there, that can we apply the closed loop, the 3D simulation in case of the laser forming?
For laser forming, we didn't try. You're talking about laser forming, for example, let's say we didn't try for forming processes, stamping processes, if I understand correctly. Mostly we use it for assembly processes. Perhaps maybe Taylor blanks used for forming, but nope. At this moment, we do not. But it will be an interesting problem, of course. Mm-hmm.
There's some questions in there. What is the input parameters for digital twin? Is it the established simulated model whose entire geometry is known?
Okay, there is actually very good questions. And then, as you very well known, the final geometry is not known in the beginning. So we are moving with so we have a few stages actually, which we are going, because this was one of the scalability, which I use it as a geometry, but starting, for example, from coupon, looking from the simplified surrogate geometry, going to surrogate geometry, which is representing the product, but might not be the same geometry as final product, and finally going to the final product. So this actually was intriguing to us, exactly the scaling on the geometry sides from oversimplified geometry as a coupon, surrogate geometry, and so on. This test which we did actually was geometry was switching continuously, and even final geometry was in the last moment actually. Yes, so this we have a capability to do it on this different level of geometry, and we are enhancing the simulator by adding basically the components, but not replacing it from beginning.
So there was one more part of this question. That what are the criteria imposed to detect any damage in a digital twin component? Okay,
so we are kind of maybe from point of view of defects, which we take into consideration. We are starting from the standard, if they're available. So from the requirements, from the OEM. So for example, in welding considers probably 14, 15 different requirements. Let's say pores, cracks, width, how wide is basically nugget, if you're not familiar, depth, penetration. Sometimes the shape is also important, concavity, convexity. So there is a different requirements I just bring into your welding itself. The similar requirements are coming from the dimensional or geometric tolerances. So we are taking into consideration. Then defects, actually, what we mean can be understood because we are not looking at the defects only in terms of welding would be easier in terms of defect definition, but we're also considering Six Sigma variation. So for example, variation of the shape. So we take the geometrical shape of the components, and the geometrical shape has a variation which is, for example, acceptable or not. So we are reducing the variation overall as well. So that's actually, but using industrial requirements in general.
I don't think any other question is there in the chat box.
There is one more, I think. There is uncertainty while dealing with digital twin.
Oh, I can't see that one. Yeah, please, can you please take the question once again?
So from uncertainty point of view, this probably is a whole beauty of the problem to deal with, at least from academic point of view, and a nightmare from industrial point of view.
Yeah.
Because, uncertainty, I would maybe, if I understand the question correctly, I would divide it into two levels. So we are dealing with imprecision meaning lack of information in early design stages. Somebody asked about the geometry, it's one example. So we do not have a final geometry of the product. So this, I would call it imprecision. And then uncertainty, meaning we know already all parameters. So imprecision, I don't know something. I do not know parameters, for example. In uncertainty, I would say we know the all parameters, but we do not know the variation range. So there is some uncertainty in terms of the variation of the parameters. So we are considering the variation, yes. So whole beauty was considering the variation on a couple of levels. One level was part variation. So we do not assume that parts are coming ideal, design nominal, but we are considering basically variation of the components. If we know the variation, then we are including it. If not, we are simulating variation as well. So starting from this, so for example, if I don't know anything about the past production, because everything is quite different, then we use the tolerancing, and then we assume, for example, let's say specific ranges, and then we are simulating the parts, generating the part with errors. If we know from historically similar parts was made before, and we know the variation, we are including this variation into the simulator as well. So this is actually just example of uncertainty. This actually we are linking, for example, components part variation to the fixturing, and then we are designing the process of fixturing based on this part variation, batch of part with variation. And then actually based on that even, we try to minimize, for example, some gaps in case of welding, that's a gap between the components, but from simulator, we know what gaps we can achieve or we can get. And then based on this gap which we get, we try to see how to how to match it with the process to be able to have a robust process under the uncertainty. So the logic is how to make a good assembly with bad parts. I'm exaggerating a little bit, so maybe not exactly this way, but how to make a good assembly with error as embedded, basically in the components and in process. Mm-hmm.
I think there is no other question, yeah. And we are almost at the end, yeah. So,
there's one more question. Should I answer? Or I don't know how many we have.
Yes, please. Yeah, please go ahead. Yeah.
There is a question talking about the. Can you give example of original new methodologies like we had developed Six Sigma at Motorola, developed in UK, Europe, especially the French aerospace industry? Okay, so I think somebody from Motorola Six Sigma coming asking for any Six Sigma related methodologies. So in short, for example, I would say like this: there is a what we have it. I don't know if you are familiar with 8D model, what Ford in US was promoting for some time by saying that going from the data until let's say root cause analysis and going to the corrective action. So what we have right now, we are having this 8D, not all steps, but root cause analysis and CAPA, corrective action, preventive actions, done as analytics right now. So not necessarily before, it was done mostly through the guidelines in industry saying how to handle it, but people was doing it. So you have to have experience. So we are trying to say we can do this with the analytics based. So that's actually logic, which I would probably mention.
Yeah. So thinking of the time constant, we'll stop reading. The last question is from Mr. Sudip Dey. Is there any specific software you are using for digital twin related work?
Mm-hmm. Okay, so from a point of view, initially we tried to use the different commercial software, but then we realized very quickly that commercial software has a limitation in terms of capability and is not open to what we needed. So we have developed our own software, which is a MATLAB based initially, which looks at the different, for example, part variation. So we are simulating basically in our own software. For example, let's say if we did this, try to use the FEM simulator for some features, for example, for laser welding processes, we couldn't. They don't have a dimple, for example, models. They have a number of features which are missing. So we couldn't use, for example, the commercially available software like FEM software. Therefore, we develop our own software, which we are able to use it right now. Similar situation was for variation simulation. Similar situation was, for example, from AI tools. So there is a lot of different AI tools right now available as a generic toolboxes, but they are not fitting, for example, to three-dimensional shapes as we needed in assembly processes. So we develop our own software, methods first, and then software, which allowing us to model for example, let's say AI model, which allowing us to describe basically the part errors. So no, we don't use too much commercial software, except basically CAT model with the different inputs.
Yeah, so, thank you, Professor Ceglarek. It was a very nice, the webinar. We are really grateful that you have taken out time out of your busy schedule and all. And what I see is that there is a lot of similarity with the activities of your group and the activities of the Center of Excellence in Advanced Manufacturing Technology at IIT Kharagpur. So I'll be very much interested to work with you, in future, in the field of robotics, AI, ML, in developing digital twins and all. I think that will be very fruitful collaboration if we work together, because there is a lot of synergy.
I'm looking forward. Yeah, we'll be very happy to work with you. And also, if there's any questions, if somebody want to ask, feel free to just to contact me.
Yeah. So, once again, thank you so much for being, present here today and enlighten us about the digital twin and all. Thank you so much for it.
Thanks a lot, and I appreciate your questions, invitation, and the very good questions coming.
Yeah. So I request Ananta to let us know about the next speaker. Next big speaker. Professor Gilrich will be talking about high productivity welding process for pipeline construction. That is on August 28 and 8:30 p.m. Indian Standard Time. Then in the month of September, we are scheduled with Dr. Dipankar Basu and also Dr. B.P. Gautam, September 4th and September 11th, respectively. Thank you all for your presence tonight. Thank you. Bye-bye.